Welcome to this comparison of SCS results with an example taken by Joints in Steel Construction Moment Connections published by the Steel Construction Institute. The worked example in Appendix 1 deals with bolted end plate design. Let's set up data starting from members. We should note that member properties are a little different from the book, likely due to the fact the book uses an older version of standard BS4. Instead of editing the database and adding a specific custom property, which is shown in the video Base Plate Design according to AIC Seismic Design Manual, let's show how SCS can directly import into the DB section properties that are saved in a file. If we open validation files, we find this example among others you might check. We can also open the file between latest files. Please observe that SCS keeps on record all past files to quickly reload old configurations. Opening the file, we see that two custom properties have been loaded. These two sections were also automatically inserted into the DB. To compare SCS results with the book results, let's generate the T-Stub report. Click on this button. This report is also included in the general report when any of the full report option is selected. Match of results is very good. Excellent match comparison can be done also for row 3. In addition, SCS provides values for row 4, not considered in the book, and SCS gives resisting values for negative moment, not considered in the example either. The book estimates 419 kN as the moment capacity, but SCS says this is only 90% of the capacity. The reason is that column web compression capacity is different. 1134 kN in SCS, 853 kN in the book. This happens because we have loaded the file with final data, which differ from what the book uses in this calculation. The compression stiffener is not input in this phase, and the flange weld size is assumed to be 8 mm. If we change weld value, we get the same result of the manual, that is 100% capacity. Shear force check also provides 100% capacity as expected. One seems to be okay and the other doesn't because of decimal rounding. About column web stiffener, we can re-input values to match the example. It must be pointed out that SCS considers for stiffeners a larger area, given by half flange width, less toe radius, and half web thickness. This is done to avoid an excessive number of input data. SCS value is therefore slightly different. The book then deals with backing plates, which can also be set in SCS. Column size needs to be changed to compare with the book. Match of results is excellent as in the previous section. The only minimal differences are due to a different toe radius in the database. It's enough to add an equivalent section in the DB to have a perfect match of results. The full depth tension stiffener can be added on top, and intermediate half depth stiffeners can be inserted between both rows. Since the connection is double-sided, web punish shear is not a design consideration, as it is explained in SCS Manual, paragraph 27.4. SCS suggestion, though, is to conservatively design a connection satisfying this requirement. The book too designs a 15 mm supplementary web plate for the original column size. At page 97 of this lengthy example, the book designs a Morris stiffener. Column size is different and the beam is hunched. The book doesn't provide exact data for geometry, but we can set up 330 mm haunch and a 15 angle for the beam. Required load is a web-bound shear force of 1,344 kN, which means a bending moment of 1,164 kN. 10 mm Morris stiffener satisfies the book request. The book doesn't provide solutions for the other limit states, but solving the whole problem can be easy with a tool like SCS. To accommodate mean flange compression, we can increase haunch flange blade. To increase the moment capacity, we can see from the T-Stub report that the issue is on the column side, and therefore increasing plate thickness cannot help. It could be useful to increase both sides or both classes, since stiffening is already set up, and we don't want to change column flange thickness. Increasing haunch depth helps too. Then welds can be modified to satisfy all the requirements.